So let's talk about the Fermi function. Now, electrons are special particles which are called fermions, which have spin. Okay, up spin, down spin. So they follow a particular type of statistics, which is called Fermi-Dirac statistics. Now, what is the meaning of the statistics and what is the Fermi-Dirac function? We have talked about the number of states in detail. How many available states are there? So that is given by the density of states, right? But whether the electron will occupy that state or not, or whether the hole will occupy a state or not, density of states won't tell you that. Density of state means you have these available states and that's it. Occupancy of that depends on the Fermi statistics, okay, or the Fermi function. So Fermi function gives you the probability that a particular state will be occupied. It is there, but whether it will be occupied or not, there is some probability. Okay, so that is given by the Fermi function. Okay, so it is the probability of occupancy of allowed states at a given energy. Different energy levels can have different occupancy probability. So it's not that all the energy levels have the same probability of being occupied. Different energy levels will have different probabilities. Okay, so the probability function, it is given by this 1 upon 1 plus e to the power e minus ef by kt. Ef is a special energy level which is called Fermi level. Okay, and of course this probability, it is a function of energy. So if energy increases, what will happen to the probability? It will decrease. So higher is the energy level, lesser is the probability of that this will be occupied. Okay, which makes kind of sense because electrons will require larger energy to reach that level. If it is a smaller level, it will be easily occupied. But to go to a higher energy level, electrons need a lot of energy. Where will that energy come from? Either it will come from the thermal energy, you raise the temperature, right? So then electrons will get some energy and they can reach to higher energy levels. This has been covered in a lecture before. Okay, so at T equal to 0 Kelvin, conduction band is completely empty, valence band is fully occupied. But at any temperature which is greater than absolute temperature, you have some electrons in the conduction band and some holes in the valence band. Electron hole pairs have been created. Why did that happen? Because electrons got sufficient energy to cross the band gap. Okay, so they have reached the conduction band. Now more is the temperature, larger is the temperature, more such electrons will be able to get this thermal energy and reach the higher level. So that's why the probability should increase as the temperature increases, right? So that's why there is a temperature term also. Now if you increase the temperature, can you say that the probability will increase? Increase the temperature, so this term will become smaller, the exponential term, so denominator becomes smaller and Fe becomes larger. Okay. Okay, so EF is the Fermi energy and K is the Boltzmann constant, and it's given by this in electron volt per Kelvin. It's a very important, by the way, factor, Boltzmann factor, and you will see the implication of this K. This has a very strong implication in the devices. When I will talk about the diodes, when I will talk about especially the MOSFETs. In fact, this is the factor which limits a lot of things in the MOSFETs. The speed of the MOSFET, okay, the power supply which is needed to switch the MOSFET. All of that can very heavily depend on this K. So it's a very important factor. And where is it arising? What's the origin of this? We did not see this K factor. By the way, this is not the wave vector, it's a Boltzmann constant, so don't confuse. Of course, you understand that. And this K is appearing for the first time in this Fermi function. Okay, so this is the root cause of all the things that will happen later. Okay. Now I have already told you it's a function of temperature. So let's see what happens at t equal to 0. So when I have t equal to 0, what will happen? This term is going to become 1 by 0, right? So e to the power kind of infinity, right? But it can be plus infinity or minus infinity. It depends whether my e is greater than ef or less than ef. Say if my e is greater than ef, so then it is plus infinity. So e to the power infinity in the denominator, it will make the whole thing 0. But if it is e is less than ef, so then it will be minus infinity, right? So e to the power minus infinity itself is 0. So this term becomes 0 then, and then f becomes equal to 1, right? So that's the case. If e is less than ef, it is 1. E is greater than ef, it is 0. But this is for absolute 0. So it's going to be a step function like this. But for any other temperature, what will happen? See, so this is f as a function of E minus EF. It means at 0, E is equals to EF, right? So this is the Fermi energy point. So when my E is exactly equal to EF, you get this step. And below the EF, every level is occupied. After the EF, no level is occupied. 0 probability. Okay, now I am raising the temperature. Say from the 0 Kelvin, I go to say 100 Kelvin. So you see this branch here. You see? So what has happened? Now you have a non-zero probability of being occupied at an energy larger than the Fermi energy. Okay, this is non-zero now. And the probability of occupancy at an energy less than EF, that has reduced a bit. So what happened? Electrons at the finite 100 Kelvin temperature, they moved from valence band to conduction band. Okay, or you can say, I mean, the Fermi energy is also, this Fermi function is also applicable to some other materials, not the semiconductors, just can be applicable to say metals also. So in general, electrons move to higher energy from the lower energy. So that's why the probability decreased here, but because the electrons are now coming to the higher energy levels, so probability has increased there. Okay, so this is called Fermi tail. You keep increasing the temperature, you will see there is a lesser and lesser probability here, but at the same time, you have a larger and larger probability of the occupancy at E greater than EF. Okay, so that's how the Fermi function works. Okay. Now what I want to do, I have the density of states and I know what is the probability of occupancy of that state. Say if I want to calculate the distribution of electrons. So how do I represent the distribution of electrons or holes? I have the number of states and I have the probability of occupancy. So at this energy level, say the density of state is some G, and at this energy level, the probability of occupancy is say F, right? So what is the quantity that will give me the population density of electrons at this level? I want to see actually how many electrons are there. The number of states times the probability, that gives me actually how many electrons are there in this level. Their density, right? Population density we call it, or the electron distribution or the hole distribution, whichever particle you're talking about. Okay, so now let's see equilibrium distribution of charge carriers, which can be electron or hole. So the distribution of electrons in energy bands is it's determined by the density of state times the probability, which is G times F. Okay, and for the conduction band, G will be Gc times F. Okay, and what about the holes? So this Fermi function, it gives you the probability of occupancy of electrons, not the probability of occupancy of hole. Okay, but what will be the probability of occupancy of holes? Whenever an electron is not occupying a level, then I call that level as hole. So it will be the probability of electron not occupying the state, which is 1 minus f. Maximum probability is 1, right? Occupancy probability is f. So what will be the probability that it is not occupied? 1 minus f. So probability of occupancy of hole is 1 minus f. And that's why you want to calculate say the distribution of holes, that is GV times 1 minus f. Okay. Now let's draw this. Right, we know GC, so GC or GV, they have under root of E dependency, and F we know it has some exponential dependency, 1 upon 1 plus exponential of E minus EF by KT. Let's see how it looks like. So this is something we call energy band diagram. So whenever we draw conduction band, valence band edge, so this is the conduction band edge, valence band edge, and say somewhere here is your Fermi level. Fermi level can be at various places depending upon some material properties. Okay, the Fermi level can be up, down, in the middle, inside the conduction band, inside the valence band. But say the Fermi level is here, just an example. So if this is the case, let me draw the density of states of the conduction band and the valence band. So this is the energy axis. Okay, if I go in this direction, the energy of the electrons is increasing. So what is this density of state as a function of energy? So the x-axis is this. I mean, it is a rotated x-axis, or you can say y-axis here. So this is my energy axis. The density of state is under root. So that will look like this. I've just rotated that plot that we saw. And similarly, the GV, that will look like this. Right? This is under root of EC minus E proportional to, and this is proportional to under root of E minus EC here, and here EV minus E. Yes, now what about the Fermi function? So Fermi function, this is my energy axis. We know that this Fermi level, below the Fermi level you have almost 1, and after the Fermi level you have this tail. And what will be the 1 minus f? 1 minus f will be exactly opposite. So here you have 1, and when you go below the Fermi level you have 0, because 1 minus 1 is 0 here. Yes, now multiply this thing. See, let's do first for electrons. So density of states of electrons and the Fermi function, this tail. This is exponentially decreasing, and this is a square root increasing function. If you take the product, so initially it will increase, but because of this exponential later it is decreasing. So it will decrease like this. So this is the product. Okay. Similarly for GV times this 1 minus f, what will be that? So for 1 minus f, tail is like this. So multiplication of this and this tail, it will give you a peak here. But you can see that this peak will be higher compared to this peak. Can you identify that? Why that will be the case? See, because this Fermi level is here, so this distribution function is shifted, right? At the Fermi level, you get half probability actually. If you put E equal to EF, so 1 upon 1 plus E to the power E minus EF. E is equals to EF gives you what? 0. So 1 upon 1 plus 1, basically half. Probability at Fermi level is exactly half, right? So you get half probability here, and then it starts to decrease. But look at for holes. So for holes, this distribution is now very away from this valence band edge. So by the time this tail reaches this level, below this is almost, very small, right? This is very small. And if I multiply this small number with this, I get a smaller peak. But here, it is appreciable. This, multiply this, you get a larger peak. So depending upon the location of the Fermi level, you can get a larger peak in the conduction band or in the valence band. Say if I would have shifted this Fermi level near the valence band, what would have happened? This peak would have increased and this peak would have decreased. Okay, it is important. Yeah. Okay. So let me show you that. So this is the case when the Fermi level is exactly in the middle. So then you get similar peaks. Of course, now it depends upon what is the density of state in the valence band and the conduction band. Usually the density of state in the valence band, it is a little smaller compared to the conduction band. So that's why this peak is a little smaller, but they are comparable. But when you have the Fermi level closer to the valence band, you see this is a larger peak, this is a smaller peak. Okay. So location of the Fermi level is very important. How do we control the location of the Fermi level in the devices, say PN junction, MOSFETs, or any device? We control the location of the Fermi level by applying some electrical bias, some electric field, or some electric potential. So with the electric potential, we can actually tune where this Fermi level will be, and that's how we change the distribution of electrons in the valence band or the conduction band. Okay, say I have a material in which my Fermi level is closer to the valence band when I don't apply the bias. But with the application of bias, what I can do, I can bring this Fermi level closer to the conduction band. Basically, I can totally invert the material. So this material had larger number of holes. It's called P-type material, right? So you can make the P-type material, electrically you can convert into N-type material by the movement of the Fermi level. This is exactly what happens in a MOSFET. Okay? This is exactly what happens in a MOSFET, in a field effect transistor. Okay, so we'll talk about that later. So now let's look at, so we have seen the distribution of charge carriers, but now let's try to evaluate what is exactly the number of electrons per unit volume in a piece of semiconductor. Number of electrons, number of holes per unit volume in a piece of semiconductor. So actual number. Right? Distribution is fine, so it's population density, but I want the actual number. So what will be that? Okay, so number of electrons per unit volume of the semiconductor occupying the levels between E and E plus dE, we know that it is GC, density of states, times the probability, right? But you will also have to multiply with the dE, because density of state is number of states per unit energy. But you don't want per unit energy, right? You want the actual number. So it is this dN by dE into 1 by volume of the sample. So the dN is the number of states between E and E plus dE, right? Not dN by dE. So you will have to multiply with dE here, so that you get this dN, number of states between E and E plus dE, and those number of states if you multiply by F, so that gives you the number of electrons that are there between E and E plus dE. Okay, but this is not the total number of electrons. See, the energy of electrons can vary in the conduction band. So the electron, if it is closer to conduction band, it's having lesser energy. If it is away from the conduction band edge, it is having a larger energy. So what you will have to do, you will have to sum up all of these electron numbers, right? How do we do that? We know that because the number of states are very large, so instead of summation we can use integration. So what you have is this. So you integrate this GC into FE into DE over, from EC to infinity. So you go from the conduction band to higher energy, up to which energy? Infinite energy. By the way, the width of the band is not infinity. Okay, do you remember these plots? So we had this, right, this, and this. Okay, so one band is not infinite width. So you are somewhere here, say EC. Actually what you should do, if you are only in this band, you should only integrate over this, and say some electrons are also here, so then the second band, the third band. But usually the width is so large that we can simply assume that it is EC to infinity. Okay, so we actually, what happens, most of the electrons will not be here, they will be around EC. So even if I am integrating from EC to some width, I'm fine. Okay, just to simplify the integration, I'm just putting the infinity there. Okay, whatever. Okay, so this is not the reality, but we do it just to just so that we are able to integrate this thing. Otherwise it will be very complicated. Okay, now GC, we know GC. What is GC? So for 3D I know GC is this, and here you see Mn star, so density of state effective mass. So this is where the density of state is going to play a major role in the calculation of N, density of state effective mass. And then what is my F? F you know. So F is 1 upon 1 plus e to the power e minus ef by kt. So this is coming because of the F, this is coming because of the G, and now you have to integrate this thing. Now this is not a very simple integration to solve. In fact, there is no analytical solution of it. Okay, so but you can get a numerical solution. But let's try to simplify it a bit, and then we'll make some approximation so that we are able to integrate. Okay, so what I can do, I can make some substitutions and define some quantities. So let me define a variable eta c, which is EF minus EC by KT. So for a given EF minus EC by KT, this is some constant. It's not a function of energy, right? Integration is over energy. And EF minus EC by KT, it's constant basically, as far as the energy is concerned. And let me also change the variable of integration. Let me put the variable as E minus EC by KT. Okay, you can change the variable of integration. Yes, what that will do, that will change your limits, right? So when E is equals to EC, so this will become 0. So limits will now become 0 to infinity. When E is in infinity, this zeta will of course be infinity. So after doing this, you can do the mathematics yourselves. What happens, you get this thing, right? So this under root of E minus EC gives you this under root of zeta, and then 1 plus e to the power, this is zeta minus this eta. So basically you do plus EC minus EC here, manipulate a bit, so you will get eta c and this zeta. Okay, and then there is this multiplication factor which is coming because of the density of states. Now what we can do, we can define that outside multiplication factor as this NC, and that integration has a special name. This is called Fermi integral of order half. Okay, so NC is that multiplication factor that you got, and this NC is also called effective density of states, not the density of state, effective density of states, and it's a particular number for a given material and temperature. What does it depend on? It depends upon the material property, which is Mn star, density of state effective mass, and the temperature. Okay, and then you also have this integral, Fermi-Dirac integral of order half, and this is a known integral in mathematics, and you can solve it numerically. So numerical solution is available, but analytically you can't do. I mean, you won't get an explicit expression. Okay, so when you say have these simulators like TCAD, if you know, so it will give you option. You want to select this full Fermi-Dirac statistics, or you want to make approximation. So approximation will be called Maxwell-Boltzmann statistics, which we will see in a moment. So if you say select this, so the simulator will inside have some way to calculate it. Okay, so actually this can be expanded into a series, and how many terms you want, that is usually already there in the simulator, say 40 terms, 50 terms, you know. So that's how they calculate it numerically inside the simulator. Okay, but if you want to do some hand calculation, you know, it will be difficult. Okay, but this is more accurate, of course. So this is your N, electron density, number of electrons per unit volume. Okay, I can also calculate number of holes per unit volume. So it's the same expression, but what you will do, you are going from EV to minus infinity, right? Or you can say minus infinity to EV, because you are going inside the valence band now. So minus infinity to EV, GV, density of states of the valence band, times the probability of occupancy of hole, which is 1 minus F, integration over energy. You can plug in the similar, you know, things, GV, expression of GV, FE, and then you will see that you get a very similar expression to what you get for electrons. So P is equals to some NV into, again, F half of eta V. So here you had eta C, which is EF minus EC by KT. Okay, it means this integration, it will depend upon this eta C value, but here the integration depend upon eta V value. What is that eta V? EV minus EF by KT. Okay, so this integration depends upon the difference between the conduction band and the Fermi level, eta C, and for the holes it depends upon the difference between the valence band H and the Fermi level, and of course the temperature. And again, NV will have very similar form to NC, but the only difference will be this Mn star will be MP star there. So that's there, right? It's a function of material property and the temperature. And it's called effective density of states of the valence band. So of course for the hand calculation it's going to be difficult. Yes, in a simulator you can do that, in a computer, but let's, you know, to simplify, so that we can do some hand calculations, we can, you know, derive some expressions later on. So let's simplify these things. So then the next approximation that I'm going to talk about, it is called Maxwell-Boltzmann approximation. It's basically the approximation of that integral that you have. Okay, so you want to simplify some terms in the integration so that it becomes possible to calculate the integration as an explicit expression. So what you have is Fe. Fe is equals to 1 upon 1 plus e to the power e minus ef by kt. Right. What if my exponential is much larger compared to this one? Then I can neglect this one. Yes. Say my energy E, it is larger than EF. Okay, and it is so large, I mean it is large enough such that I can neglect this one. Then I can write F is equals to e to the power, I mean this is neglected and this will go up, so there will be a minus sign here, e minus ef by kt. This is called Maxwell-Boltzmann statistics. Okay, this expression, exponential of minus of ef, e minus ef by kt. Now, but how large my E should be from EF so that I can make this approximation? So rule of thumb is, if my EC minus EF, it is greater than 3 kt, it means e to the power, if I have say 3 kt here at least, so e to the power 3, right, kt will cancel, so e to the power 3, that will be I think approximately 10 or something, right? So in front of say 10 you can neglect this one. Okay, it's not a hard and fast rule, you can pick your own limit, say 5 kt if you want to be more accurate, right? But minimum gap usually that is acceptable to use this statistics, it should be 3 kt at least. So when I do that, I mean, so what I want to say is that EF and EC, they have a gap of 3 kt or larger. So it means either my EF will be 3 kt below or larger than that. It should not go beyond this. It should not go beyond this, and certainly not inside the EC. Okay, so when you go above this EC minus EF by 3 kT, then I call that my semiconductor is degenerate. Okay, and when I am within this limit, my EC minus EF is greater than 3 kT. My Fermi level is below this. So then I call it as non-degenerate. So this is for the conduction band I'm talking about. For the valence band, you can make same approximation. So here you have EF and EV. So your EF should be larger than EV by at least an amount of 3 kT. 3 kT or larger. Okay, so your EF can be here or here or here, but it cannot certainly be below this or inside this. So if that's the case, you can't use this. Then you will have to use the Fermi-Dirac statistics. There is no option. Otherwise, your answer will be inaccurate. Why it will be inaccurate? Of course, you won't be able to neglect this in terms of 1. Okay. So this will then again become the degenerate case. So this is your non-degenerate territory, and beyond that you have degenerate. Okay, so let me now calculate with this simplification my electron density, and electron density will be Gc into F, but this time the F is e to the power minus E minus EF by kT, and then this under root is coming because of the Gc. This is integrable. Okay, how you do that? So let me put this E minus EC equal to X, so that will change the limit of integration. There will be some terms outside, so this will be 0 to infinity under root of X e to the power minus X by kT. This is doable. I think this E will also change to some X. Probably this should be dx, I think, not E. Right, under root of X into e to the power minus X by kT. You can integrate it using integration by parts. Again, do it yourselves. But finally what you get is this. Okay, some explicit expression. In that explicit expression, what do you have? You have this e to the power minus of EC minus EF by kT, and then all the constant terms I have plugged that into one single term, which is NC. And this NC is the same NC that we got for the Fermi-Dirac statistics. You can check it. Okay, if you combined all of this, you will get the same thing. So N is equals to NC into e to the power minus EC minus EF by kT. Probably this is the expression you might be familiar with. Okay, and what does it depend on? It depends upon the difference between EC and EF. And how do I control that? I can control that in many ways. I can, there's something called doping. We'll talk about it. You can dope the semiconductor. You can change the gap between EC and EF. You can increase or decrease the temperature. You can change the gap between EC and EF. You can apply some potential, electrical potential, and you can change the gap between EC and EF. So several ways, right? And electron density will depend upon that. NC is the same thing, depends upon Mn star and kT. For 300 Kelvin, for silicon, NC is 2.8 10 to the power 19 per centimeter cube. So this number, you should have an idea about the order of this number. So 10 to the power 19 per centimeter cube, that's the number. By the way, what is the density of atoms in silicon? I gave a question about that, I think, in paper, in the midterm. So 5 into 10 to the power 22 atoms per centimeter cube. So compared to that, this is 10 to the power 3 less, roughly. Okay. So whenever my electron density, you can also have this thumb rule that whenever my electron density is approaching these levels, 10 to the power 19 or beyond, my semiconductor will not remain non-degenerate, it will become degenerate. Because only when I have EC and EF very close, they will be able to generate this much high electron density. If I have an electron density, say 10 to the power 16 per centimeter cube, 17 per centimeter cube, I can safely use this Maxwell-Boltzmann statistics. Okay. Same thing you can do for the holes. So for holes, 1 minus F is 1 minus of this. again you can simplify this, assume that E minus EF is much larger than the KT, and 1 minus F can be approximated then by e to the power E minus EF by KT. So this time there is no minus here, there is this plus, okay, because of this 1 here. So for the holes you can do the same thing, right? I won't go through this, but in case of holes you have P is equals to NV into e to the power EV minus EF by KT. So it depends upon the difference between EV and EF. Again you can control that using doping, temperature and bias. Now what is this NV? What's the order? The order is the same. So 1.04 10 to the power 19. So both are 10 to the power 19 per centimeter cube order for silicon. For different materials it can be different. But usually it will be a high number, 10 to the power 19 something. Yeah, of course if you lower down the temperature it will reduce. If you increase the temperature it will increase a bit. But it does not have very strong temperature dependence. So it is T to the power 3 by 2. Yes, it is some temperature dependence, but it is not something like exponential temperature dependency or something like that. Okay. So not a very large temperature, very heavily temperature dependent term. Okay, now let's talk about the Fermi-Dirac versus Maxwell-Boltzmann. Now this plot will make everything clear to you. If I draw Fermi-Dirac, I know my curve looks like this, right? So it starts from 1, probability 1. At EF, the probability is half, and then you have this tail, right? Now say my conduction band is somewhere here. It is larger than EF, and there is some sufficient gap between EF and EC. And this dotted line shows the Boltzmann approximation, which is e to the power minus E minus EF by KT. Okay, so in one case you are plotting the Fermi function, and this is e to the power minus E minus EF by KT. And of course this is a decreasing exponential, so that's why this. So this is normal exponential. But you can see that they are only matching when I am in this region. So whenever I am this region, Fermi-Dirac or Maxwell-Boltzmann, both are similar. But when I am going closer to the EF, say if my EC is not here, if it is say here, you see the error now. Fermi-Dirac statistics, which is the actual one, it is here, but the Boltzmann is giving you an overestimate. The closer you get to the EF, the error becomes larger. In fact, at EF, this is just blowing up. Very inaccurate result it will give you if you have EF and EC very close to each other. Maxwell-Boltzmann will give you heavily inaccurate results. Okay. So let's move on. Now let's talk about intrinsic semiconductor. Probably you already know this. So intrinsic semiconductor. What is an intrinsic semiconductor? Anyone? A pure semiconductor, right? Which does not have any impurity, no foreign atom, right? So that is the intrinsic semiconductor. So if I have silicon, so I am only talking about silicon, just the silicon, perfect silicon, no foreign atom, nothing. So that is called intrinsic semiconductor. Okay, it will have zero impurity, or if the impurity is there, it is negligible. So that is your intrinsic semiconductor. Now at t equal to 0, I can draw this, this bonds and these silicon atoms. So this type of diagram. One of the lectures, again, previous lecture covered this already. Now at t equal to 0, all of these bonds are intact. So for silicon atom is going to make these 4 bonds with the neighboring silicon atoms. Actual structure will be 3D, but I am just showing it in the 2D plane. And all of these bonds are intact because the electrons don't have any energy to break out of these bonds. But when you increase the temperature in an intrinsic semiconductor, what happens? Some of these bonds will break and these electrons will go to higher energy states in the conduction band, and they will create a vacancy in the bond, and that is called hole. Right? So it's a visual representation of electron and hole. So in terms of energy band diagram, you have a transition of electron from the valence band to the conduction band, and it creates an electron hole pair. Right? Now at any finite temperature, there will be some electrons in the conduction band, some holes in the valence band. What will be their density? So their density must be equal. Yes, because they are created in pairs. In intrinsic semiconductor, they are always created in pairs. So whenever you break out of bond, you create electron, one hole. Okay, there is no way for an electron and hole to have different density. So because they are created in pairs, so N is equals to P, and let me denote the common density by Ni. Ni is also called intrinsic carrier concentration. Right? Electron and hole, they are called carriers. Why carriers? Because they carry charge, they carry charge and they can move. Okay, so they can carry the charge from one place to another place when you apply an electric field, because they have charge. So they are called charge carriers, and that's why this is intrinsic carrier concentration. Okay, so what is this number then? Let's calculate. So intrinsic carrier concentration, I'm going to be using Maxwell-Boltzmann approximation from now on. Okay, just for the simplicity. So N is equals to, we know that Nc into e to the power minus Ec minus Ef by kT, and P is given by this expression, which depends on Ev and Ef. Now N into P, we know that, let's multiply these two, N into P, so that will be Nc Nv. This Ef and Ef will cancel, so that will make it Ec minus Ev by kT. What is Ec minus Ev? This is the band gap, Eg. Right? So Nc Nv e to the power minus Eg by kT. And I know that Np is equals to what? N is equals to Ni, P is equals to Ni. So Np will be Ni square, and Ni square will be this Nc Nv e to the power minus Eg by kT, and Ni will be under root of that. So my intrinsic carrier concentration, it heavily depends on the band gap, the temperature. I'm not talking about this. Of course, it depends on Nc and Nv also, but it depends exponentially on Eg and temperature. So if I have a semiconductor which has a larger band gap, Ni will exponentially decrease. If I change the temperature, say I increase the temperature, what will happen if I increase the temperature? Ni will exponentially increase. You increase the temperature, so this e to the power becomes less negative, means it increases exponentially. So that increases the Ni exponentially. If you reduce the temperature, Ni will reduce. Okay. Now for silicon at 300 Kelvin, Nc is this, Nv is this. Eg for silicon, it is 1.12 electron volt approximately. Plug these numbers here, you get Ni at room temperature 1.5 10 to the power 10 per centimeter cube. Remember this will be very useful. Okay, at least 10 to the power 10. 10 to the power 10 per centimeter cube is the order at room temperature. Now let me calculate the position of the Fermi level. We haven't talked about the Fermi level at all. We know that it is some level, but we haven't tried to determine its position. Where is it located? Is it inside the band gap? Is it closer to EC, closer to EV, outside EC and EV? Let's see for an intrinsic semiconductor. So how do we do that? Okay, Fermi level in intrinsic semiconductor, I know that in intrinsic semiconductor, N is equals to P in equilibrium. Yes, and you can equate this expressions, N expression and P expression, and from this you will be able to calculate the EF. Okay, so e to the power this minus EC plus EV minus 2 EF by KT, that is NC by NV, and take the log on both sides, you get this. EC plus EV by 2 minus KT by 2 into log of NC by NV. Okay, so this is the mid of the band gap, EC plus EV by 2, exactly the middle, and it is slightly below the middle, minus term is there. And I know that NC is greater than NB, so this term will be positive. Okay, NC is slightly larger than NB. But NC and NB, as far as their orders are concerned, it's the same. 10 to the power 19 here, 10 to the power 19 here. Right. So this log term, it's not a very large term. And then you have KT by 2. Okay, so KT term at room temperature, that will be around 26 milli electron volt. Okay, very small number. So we can neglect this term compared to this. Okay, so EF is approximately in the middle in an intrinsic semiconductor. So exactly this diagram that I showed. It is exactly in the middle. You can draw the electron distribution. They will almost look similar. By the way, what is the area under this curve? So this is the multiplication GC into FE. What will be the area under this curve? What does that represent? Electron concentration. Right? What will be the area? Area will be the integration of this. Area under the curve is integration, right? So GC into FE dE integration, that is this area. So this is the electron concentration, this area, and this area is the whole concentration. Although the peak here is a little larger than the peak here, but the spread here is more. So overall, if you calculate the area of this and area of this, you will get equal because N is equals to P. Okay. Now quickly let's talk about the extrinsic semiconductor. Extrinsic semiconductor, as the name suggests, there will be some foreign atom in this. There will be some impurity, right? And what we do, sometimes actually most of the times we are going to intentionally put some impurity in the semiconductor to change its conductivity. Okay, to change the electron and hole concentration. So that process is called doping. And the foreign atom that I am putting inside the semiconductor, that is called dopant. Okay, there are two types of dopant. You probably know. There is a dopant called N-type dopant. So N-type dopant is going to increase the electron concentration, and there is a P-type dopant that will increase the hole concentration compared to the electron concentration. Okay, so let's talk about the silicon. So for the silicon, N-type dopant for the silicon can be a pentavalent impurity. For example, phosphorus and arsenic from group 5, they can act as N-type dopant for silicon. Now this is just for the silicon. It's not that you put phosphorus in, say, gallium arsenide and you will get some good properties. So for different materials, the dopant can be different, but it should increase the electron concentration. Now how it does that? Let's again make our bond and atom diagram. So what happens? So this is a pentavalent impurity. It means it has 5 electrons in the outermost shell. Now if you put the dopant inside the silicon, it is going to replace one silicon atom and it will take its place. But it can only make 4 bonds with the neighboring atoms. Right? 4 bonds, but it has 5 outermost shell electrons. So one electron is now unsatisfied. And it has a higher energy. Okay, a pentavalent atom, 4 are inside the bonds. So whenever an electron is inside the bonds, it is tightly held. But this electron, it is loose. 5th electron, it is not inside the bond, so it is more free to move. Right? I mean, at least it is at a much higher energy level than the electrons inside the bond. Yes? So this is basically one phosphorus atom is contributing one such electron, which is relatively more free compared to a bond electron. Right? Now, what happens in the energy band diagram? Let's see. So what happens whenever you put these pentavalent atoms, say phosphorus or arsenic, they are called donors because they are kind of donating one extra electron. Now, whether that extra electron is useful for us or not, let's see. What they do, these donors, they will contribute some energy levels slightly below the conduction band. So where are these electrons located? I said these are at higher energy levels compared to the bond electrons. Where are the bond electrons? Inside the valence band. So they must be much farther from the valence band. Actually they are very slightly below the conduction band. And how slightly below? Only 30 millielectron volt to 60 millielectron volt. Very small difference. So if you look at this EC, conduction band H, these dopants contribute these extra levels, discrete extra levels, slightly below this EC. This is called donor level. Okay, now you can see that I did not make it as a continuous line. There is a reason for that. There are discrete levels. Why? Can anyone tell me why? Why there are discrete levels? Yes, but why? So I'm plotting, say, this as a function of distance. Different places, but there is some gap, broken line versus a continuous line. So broken line has a significance. So when you have silicon atoms, say there is no foreign atom. These silicon atoms are very close to each other. They form energy bands. Energy bands are all continuous, we know that, right? And at every point in the space, you have energy band. But look at these pentavalent atoms. Are they going to form a band? No, they are much farther apart than two silicon atoms. So if I have this picture, if say one phosphorus atom is here, it's not that another phosphorus atom is here. Another phosphorus atom will be much farther. Okay. Let me talk about some numbers. So 10 to the power 22 is the density of atoms of silicon per centimeter cube. Usual doping levels are 10 to the power 16, 17, 18 is on the higher side. We never go to 19. I mean, we can go to 19 and 20 also, but for special cases, say to form the contacts, etc., we can go to high these doping levels also. But say if I am at normal levels 16, 17, 18, say let's pick 17. 10 to the power 22 divided by 10 to the power 17. What do you get? 10 to the power 5. For every 10 to the power 5 silicon atom, you only see one phosphorus atom. So they are much farther apart. Because they are much farther apart, what do? If I have an electron in this phosphorus atom and an electron in another phosphorus atom, are they going to interact with each other? No, they don't interact. That's why they have discrete levels. So this electron belongs to this electron belongs to this. Okay, at least when they are inside those energy levels. Okay, but they are not talking to each other. If they would have talked to each other, say there are a lot of phosphorus atoms, right? Then their wave functions, electron wave functions, they will start to overlap, and then you will have splitting of energies. They will form bands. We saw that. That's how the bands form, right? There should be some interaction. They are not interacting with each other, and that's why you have this discrete. Sometimes what happens when you have a large electron, this dopant concentration, say 10 to the power 20, they actually become close to each other and they form a small band called dopant band. Okay, they do form a band then, and because of that there is a term called band gap narrowing. What happens if, say, I have splitting of these bands like this? I mean, instead of discrete, say I have a band like this. So effectively what you have done, you have reduced the band gap from this to this. It's called band gap narrowing. Okay, but for most of the cases that we are going to talk about, we will not get into this. Okay, so this is 30 to 60 millielectron volt, but this is a very small energy. Now at t equal to 0, what will happen? All of these extra electrons will be occupying these ED levels, donor levels. There is no way for them to get to higher energy levels. They will be occupying these. But as soon as you raise the temperature, say to 30 Kelvin, 40 Kelvin, 50 Kelvin, they will start to excite to the induction band, because this energy required is very small, 30 millielectron volt, very small energy compared to the band gap. Band gap is 1.12 electron volt, and this energy is 30 millielectron volt, so very small, right? So around 50 to 100 Kelvin, in this range, all of these dopant atoms will be unoccupied and these electrons will jump to the induction band. Okay, but what do they leave behind? Now this phosphorus atom was holding this one electron in one particular level. This was not free to move at t equal to 0, but now this electron has gone to the conduction band. When something goes to the conduction band, it is not the property of that phosphorus atom alone or arsenic atom alone. Now that electron becomes available to move everywhere in the semiconductor, right? So what does that electron leave behind? If it is gone, it leaves behind a positive charge, because atom was neutral, but now an electron has left, so that becomes positively charged. So donor are going to create positively charged ionic core, we say. So whatever is left is called ionic core, or simply you can say that it is a positive charge. Okay, so this is the positive charge, and then you have the electrons. Now, can I calculate this 30 millielectron volt? Where did it come from? So there is a very simple small model we can use to calculate that. Let's calculate this through hydrogen atom model. So in a hydrogen atom model, you can only have one electron in the outermost shell and some positive charge on the nucleus, one positive charge, right? And what is the energy with which an electron is attached to the hydrogen atom? So minus 13.6 divided by n square electron volt, if you remember that, if you can recall. Right? So there is some binding energy, right? So this is basically that binding energy. This electron that is there in the pentavalent, it is bound to this pentavalent impurity with some energy. If I provide an energy which is larger than this electron will break free. So using the hydrogen atom model, I can assume that this loose electron, it is revolving around a positively charged ionic core of the phosphorus atom, right? And I can use this Bohr's model, and energy is given by this minus 13.6. Let's say we are talking about the ground state energy. So minus 13.6 divided by n square, n is equals to 1. And because you have put this dopant, so this is very important. I have an epsilon r square here, dielectric permittivity. In case of vacuum, this would have been 1. So that's why you don't see minus 13.6 divided by anything. Yeah, in case of a, say, normal Bohr's model. But here I have epsilon r square here. It is, where will the epsilon come from? It will come in the electrostatic force, the Coulomb's law. 1 upon 4 pi epsilon into q1 q2 by r square. So that's where it is coming from. Why? Because I have put this phosphorus atom in a medium. What is the medium? Silicon is the medium. Okay, and then you also have m star by m naught, the ratio of the effective masses. Now what this epsilon r square is going to do, say if this is vacuum, this will be 1. So you have minus 13.6 electron volt, that much amount of energy you require. It's a very large energy. Okay, but when I have epsilon r square here, because of this energy is going to become very small. What is epsilon r for the silicon? Relative permittivity of silicon, what's the number? 11.7, right? Roughly 12. So you are dividing this 13.6 by 144. Okay, calculate it, it will come very close to these numbers. So it will come in the millielectron volt, specifically minus 26 millielectron volt. So it reduced your energy from 13.6 to simply 26 millielectron volt. And that's why if you have, say, a phosphorus atom in vacuum, it's not going to lose electron. Okay, it's minus 13.6. But when you put that in a medium of silicon, then it can easily lose that electron. Okay, because these silicon atoms are also creating some electrostatic force which is making this happen. For example, you have, say, a table salt, NaCl. You put that in air, it's solid form. Put that in water, everything will break apart. Why? The dielectric constant of this water, it's 80. So whenever you put NaCl inside the water, the force between the positive charge and the negative charge, Na plus and Cl minus, it becomes 1 by 80. 1 by 4 pi epsilon into Q1 Q2 by R square. Okay, so it's that electric force or electrostatic force of the medium that is making this happen. Okay, so let's quickly finish this up. So p-type dopant, let's talk about. So p-type dopant, obviously it's going to increase the hole density, but what is the p-type dopant for silicon? So it's usually boron. Aluminum can also be there, but practically we usually use the boron. Okay, what will it do? So this will be a trivalent impurity. So it will only make 3 bonds with the neighboring silicon atom. So it will replace the silicon atom, makes 3 bonds, 1, 2, 3, and one of the bond is not complete. This bond only has 1 electron and there is a 1 vacancy. So that is basically going to become a hole, right? So 1 trivalent impurity, it's going to contribute 1 hole. So what will happen? What can happen? Say there is a neighboring atom here. So there is a neighboring electron here in this bond, right? So what can happen? This electron can transition to this and form a bond, and in turn there will be a vacancy that can create here, that can be created here. Okay, so that's how this vacancy can move also. It's not that you put the boron atom here, the vacancy will stay there. No, from a neighboring silicon atom, silicon bond, 1 electron can jump to this state, so this bond will be fulfilled, but the vacancy will be created there. So this vacancy can move. But again, there is some energy that is required for this vacancy to move. And what happens? So these trivalent impurities, they create some energy levels similar to the pentavalent impurities, slightly above the valence band, like this. Discrete levels again. Okay, and all of these levels have, basically they are empty levels. Okay, now what can happen? Again the difference is 30 milli electron volt to 50 60 milli electron volt, because this difference is very small. An electron from the valence band can easily jump here at any non-zero temperature, from 50 Kelvin to say 100 Kelvin. In fact, all of these levels will be occupied. So this is called acceptor atom, because it is accepting an electron, right, and it is fulfilling the bond, but in turn that will create a hole in the valence band, an empty state in the valence band. Okay, and the energy required is very small. So same thing will happen here. Okay, so and of course in this process this will become negatively charged. So it will have a negatively charged ionic core. Acceptor will be negative charge and the donor will be positively charged. So last topic, this NP product. We have seen this NP product for intrinsic semiconductor. We know that, right? NP will be equal to Ni square because N is equals to P. But NP equal to Ni square is actually true in general, not just for the intrinsic semiconductor. If you don't apply an electric field, it is still equilibrium, there is no current. So NP will still be equal to Ni square, provided there should not be any current flowing in the semiconductor. When the current flows, we'll see later what happens. Okay, so N is equals to this. We know that Nc e to the power minus Cc by Ef by Kt. P is equals to this. Let's do the product. So Np is equals to, again, Nc Nv into e to the power minus Eg by Kt. Ef will cancel. Right, so it's the same thing that we saw in case of intrinsic semiconductor. I mean, whether it is intrinsic or extrinsic, my expressions will not change. as long as it is equilibrium. Yeah. Now I know that this quantity Nc Nv into e to the power minus Eg by kT, this was Ni square, right? We just saw that. So we can simply replace this by Ni square, and Np is always equals to Ni square. This is also called law of mass action. Okay, it can be derived in some other ways also, by using some different arguments, but you get the same expression. Okay, so that's it for today. So see you next week. Thank you. Wait for the attendance. So last time we talked about doping, carrier statistics in equilibrium, and we evaluated the expressions of electron and hole densities, and then we showed that NP product remains the same, N into P equal to Ni square, whether it's an intrinsic semiconductor or extrinsic semiconductor. So let's build upon that. So there is a concept of charge neutrality in semiconductors, and this will be useful when we study the devices, for example diode or MOSFET. So whenever you are solving a device, you need to solve its electrostatics. You apply some potential, say some voltage, and then you want to see how is my distribution of the potential, because see, potential determines the electron and hole densities. Why? Because you have conduction band and valence band, right? So they are kind of potential energies. We'll talk about it a little bit later. So conduction band and valence band are related to the potential. So if your potential varies, your conduction band edge and valence band edge will also vary. It means your electron density and hole density will also vary. Okay, so the distribution of the carriers within the device, it heavily depends upon your potential profile. So to do that, what we do, we apply Gauss law, right? So we know that Gauss law is used to calculate the electrostatics, or its differential form, which is typically used. It's called Poisson's equation. You may know about it. So it's a differential equation. How does it look like? So it looks like this. If you have, say, a one-dimensional semiconductor, so Poisson's equations means d zeta by dx, zeta is the electric field, is equals to rho by epsilon. Epsilon s is the permittivity of the semiconductor. Okay, for silicon it will be some 11.7 epsilon naught, right? Permittivity of the free space is epsilon naught. So now electric field is obviously related to the potential, right? Electric field is minus dV by dx. V is the potential. So this equation is going to be used for calculating the potential profile. We'll do that later. But and what is this rho? Rho is your total charge density. So total charge density is composed of what? You have electrons, right? They carry negative charge. You have holes, they carry positive charge, right? And then what else you can have in your device? You can have dopants, right? Because after donating, say, the electron, these donors, they become positively charged. After accepting the electrons, acceptors become negatively charged. So they are fixed charges. Electrons and holes are mobile charges. If you apply the electric field, they are going to move. But these ionic charges, ionic cores of dopants, they will remain fixed, but they do carry the charge, and that should appear in the rho. So what is rho then? So rho is going to be minus, rho is per unit volume. So if I multiply the per unit volume density with the charge, so that will give me the charge per unit volume. Okay, so rho is charge per unit volume. So coulomb per centimeter cube. So minus q into n is the free electron density, and minus q because of course it carries negative q charge. Q is electronic charge, 1.6 10 to the power minus 19 coulomb. Then plus qp, p is the hole density, of course, positively charged. Then plus qnd plus. Now what is this nd plus? Nd plus is the ionized dopant density. of donors. Nd means density of donors, and only that density which is ionized. You have seen that at very low temperatures, all the dopants may not be fully ionized. But at a temperature which is near the room temperature, or any temperature which is say greater than say 50 Kelvin, almost all of them will be ionized. So I'm going to simply assume that Nd plus is equals to Nd, that all of them are ionized. Okay, most of our problems will assume that. Unless you go to say cryogenic temperatures, very low temperatures, then you will have to think about it. Otherwise, you're fine. So Q into Nd plus minus Q into Na minus, you have acceptor, right? So in general, your semiconductor can have all four of them. So Na minus, right? It carries a negative charge, so minus Q Na minus. And again, Na minus is the ionized acceptor density, but Na minus will be approximately equal to Na for most of the cases. Now, from the Poisson's equations, now there are regions where electric field is 0. You can have a semiconductor in which you have some regions where zeta is equals to 0. Electric field does not exist there. So for those cases, rho will also be 0 at every point from this equation. True? If my zeta is 0, say in a particular region, so at every point of that region, rho should also be 0, because it has to follow the Poisson's equation. So that region where rho is equals to 0, that is called charge neutral region. And in the devices, these regions will exist. In PN junction also, in MOSFET also, MOS capacitor. So this is a special region where rho is equals to 0. Now in that special region, because rho is 0, so this, according to this equation, so you can put 0 here. So what will be the relationship between Np, Nd and Na? So I'm assuming that Nd plus is equals to Nd, Na minus is equals to Na. So relationship will be this. Right, so total negative charge, the magnitude of the negative charge N plus Na minus is equals to the magnitude of the positive charge. Correct? Or if Na minus is Na and Nd plus is Nd, so then simply this. So this we will use many times. Okay, so now let's talk about the location of the Fermi level in an N-type semiconductor. We know that in an intrinsic semiconductor, where is the location of the Fermi level? Almost in the middle. Yes, we assume that it is Eg by 2 if you measure it from the bottom, conduction, this valence band. So exactly in the middle. But what is the location of the Fermi level in an N-type semiconductor? Okay, we have kind of seen it, right? If you remember the distribution of electrons and distribution of holes, so I talked about two types of distribution. In one case, electron distribution was larger, right? And that was the case when my Fermi function was closer to the conduction band. The Fermi level was closer to the conduction band. You can go back and check in your notes. So then that makes the distribution of electrons larger. And when my Fermi level was closer to the valence band, the whole distribution becomes larger. So we kind of already know in an N-type semiconductor where will be the Fermi level. It will be closer to the conduction band. And in valence, in say P-type semiconductor, Fermi level will be closer to the valence band because the whole concentration has to be larger. Right? But can we mathematically prove it from the expressions that we have derived? At that time, we did not know about the N and P expressions, but can we derive it? We can derive it using the same method as we did for the intrinsic semiconductor. So what we have is this. Assume that this is true. I am talking about a semiconductor bar, in which I haven't applied any electric field. Okay, so assume that it's simply a semiconductor bar and I haven't applied any voltage. So obviously, what will happen if there is no electric field? Rho will be equal to 0. It will be charge neutral. So n plus Na will be P plus Nd, of course. And we also know that in an n-type semiconductor, right, Na will be 0. Although Nd and Na both can be present, but typically, you only dope by one type of dopant. So only Nd will be there. So this Na is gone. Further, you know that in an n-type semiconductor, Nd will be much larger than P. Do you agree? It's an n-type semiconductor. Correct. Number of holes have to be much smaller than the number of electrons. Yes. So this P, I mean, you can compare it with Nd or N, whichever you like. So if I take, say, on the left hand side, this is 0. So N minus P is equal to Nd. Now I already know that in an n-type semiconductor, N has to be much larger than the P. So I can neglect P. So what will happen? N will become approximately equal to Nd. True? So for an n-type semiconductor, I can make this assumption, provided again, you are talking about the normal cases. You are not going to very low temperatures or anything like that. Okay, now also I know that the expression of N is given by this. N is equals to Nc into e to the power Ec minus Ef by Kt. Correct? And this is a negative sign. So I can plug this Nd here and it will simply become Nd equal to Nc into e to the power minus Ec minus Ef by Kt. Right, and now this is going to give me a very good idea where my Fermi level lies. I can, take everything on this side and then take the log, and then I can check where my Fermi level lies with respect to my conduction band. Ec minus Ef is basically the distance between the conduction band and the Fermi level. Correct? The difference. So let's do that. So Ec minus Ef will come out to be Kt into log of Nc by Nd. Correct. Okay, so this is the equation for n-type semiconductor. Now, whether this is larger than, say, the mid gap or below the mid gap, right? Can we determine that? So where is the Fermi level in an intrinsic semiconductor? What should I do to this equation so that this becomes the equation of intrinsic semiconductor? What is N in an intrinsic semiconductor? N is equals to Ni. So N will not be equal to Nd, it will be equal to Ni. So it will be simply replaced by Ni here. Right, so Ec minus Ef for an intrinsic semiconductor will be Kt log of Nc by Ni. Now you can compare the both. Which Ec minus Ef is larger? True? Compare 1 and 2. Which Ec minus Ef will be larger? So Ef is basically Ei, right, in intrinsic semiconductor. So just a notation here. But which one is larger? This is larger or this is larger? So Nd, what is the typical Nd number? 10 to the power 15, 16, 17, 18 per centimeter cube. It can be larger also. What is the Ni number at room temperature for silicon, say? 10 to the power 10. Much smaller. So this is much smaller. Right, and I know that Ec minus Ei is roughly the mid gap. I mean, Eg by 2. I know that. We have already proved it. Correct? So this gives me half of the band gap. This should give me smaller than that because this Nd has to be larger than Ni. So if this Nd is larger, of course this log term will be smaller. So Ec minus Ef has to be smaller than Ec minus Ei. It means if this is mid gap, this has to be above mid gap. Correct? Because Ec minus Ef has to be smaller. So you go a smaller distance from the Ec. Here you go a larger distance from the Ec. Correct? So this is going to be the location of the Fermi level, somewhere here. Now, where exactly it will be, it depends upon what? The doping. You change the doping, you move it. Yes? You change the doping and you can move it. Okay, what if I keep increasing my ND? Where will it go? Will it go this side or this side? If I increase my doping, will it go this side or this side? So EC minus EF will obviously reduce. So it has to go up. And it makes sense. It makes sense. Why does it make sense? Because EC minus EF determines the electron density. E to the power minus of EC minus EF by KT. If my EC minus EF is smaller, electron density will be larger. It is E to the power minus of EC minus EF by KT. So EC minus EF has to be smaller in the exponential so that the electron density increases. Okay, so this is for N-type semiconductor. You can do the same thing for the P-type semiconductor and you can prove it, go through the notes. Right, in the P-type semiconductor, obviously P will be approximately equal to Na, and you can prove similarly that EF will be smaller than your intrinsic semiconductors Fermi level. Okay, using the same argument, you can derive it. Okay, so this we have already seen, equilibrium distribution of carriers, right, in an extrinsic semiconductor. But at that time we did not know what is N-type, what is P-type, what is the electron hole density, where should the Fermi level be. Now we know. So we know that EF has to be here, okay, and EC, the density of state is square root, in valence band also it's square root, correct. This is the Fermi function. So Fermi distribution function, because my EF is here, so Fermi distribution function has to go through this. So this is half probability, and 1 minus F has to go like this. Now because this Fermi function is closer to the conduction band edge, so the multiplication of this tail and this will look like this, right? So this is decreasing, this is increasing. Obviously the product is going to look something like this. It's going to give a peak near the conduction band. And if you look at the valence band, because now 1 minus Fe is much farther from this valence band, right? So by the time it reaches inside the valence band, this tail is much smaller. Multiply this tail with this, so that will give you a smaller peak. Correct? So this is the distribution looks like. Now you can also see that from this distribution, most of the electrons and most of the holes will always lie closer to the band edges. It's very clear. True? This peak is much near to the band edge. This is also near to the band edge. So when we talked about, say, EK diagram, we always talked about this minimum of energy. I mean, minimum of energy of the conduction band is the conduction band edge, right? Maximum of the valence band is the valence band edge. You remember? So they make those two valleys, right? And we only cared about when I am near the extrema points. Either I am near the minimum point or the maximum point. And we also made these approximations, effective mass approximations, for example, parabolic approximation. Right, so I assume that near my extremum point, say maximum or minimum, I can approximate my band structure by a parabola. Why does that work so flawlessly? Why does it work? If I'm not going away from the band edge in the EK diagram, I know that my parabolic approximation is going to be good. If I go too far from the band edge, it will fail. But whether I am around those minimum points always, how do I determine? You can see it here. You're always closer to the band edge. Most of the electrons are near the band edge. So if most of the electrons are near the band edge, and they will determine all the semiconductor properties, that's why my parabolic approximation will work just fine. Yes, unless you apply high electric fields, you accelerate the electrons, you provide some light or something like that, excite the electrons to higher energies. That's a separate thing. But for say a first order analysis, this is good. Approximation is good. Similarly, for the p-type, it's very obvious, right? So this peak will be larger than this n-type peak, yes, because 1 minus Fe will be closer to the valence band H. Okay, so next is this is some reading assignment for you. So what this is basically, so this is a plot of the electron concentration in a semiconductor. And I'm plotting that with inverse of temperature basically, and this is log of n actually. So this is log scale and this is your linear scale, but inverse of temperature. So if you plot it, you get something like this. Okay, so if you have say an extrinsic semiconductor, you get almost flat. This is also, by the way, it is also going to determine the conductivity of the semiconductor, right? If you have larger electron concentration, say you have an n-type semiconductor and you have a larger concentration, so what will happen? Conductivity will rise. So you can say n or conductivity, although conductivity also depends upon the mobility. We'll talk about that, but this is a stronger function of the temperature compared to say the mobility. So that's why this will determine the conductivity as a function of temperature. Okay, so for extrinsic semiconductor, you can see that not much impact of the temperature, right? If I go say to very high temperatures, high temperature means because it's inverse, so high temperature will be here, correct? So as you go to high temperature, the semiconductor becomes almost intrinsic. Intuitively, can you think about it? What will happen at high temperature? Okay, what will happen here? Why this is flat? I have an extrinsic semiconductor. I have doped it. Electron concentration is already very high. True. What happens if I say increase the temperature now? Is it going to change the electron concentration too much? What will the temperature do? See, your dopants are already ionized. So temperature is not going to ionize the dopants more. That's already done. You are not in that temperature range, for example. Say you are near, say, room temperature, and then you are increasing the temperature. So those dopants are already ionized. Okay, so you can't increase the electron concentration because of the dopants. Now, what that will do, the temperature, it will create more electron hole pairs. So it will excite an electron from the valence band to the conduction band via thermal energy. But how many such pairs will be there? Say if I remove my n-type concentration coming from the dopants, right? Then how much the thermal energy alone provides me the electron concentration? Say it is intrinsic semiconductor. And now you have these thermal generation of say electron hole pairs. Electrons are getting excited to the conduction band. How much concentration does it give me? 10 to the power 10. Very less. Not very effective. Now you have doped it. Already your concentration is 10 to the power say 17 per centimeter cube. What is thermal going to provide you extra? 10 to the power 10. 10 to the power 17 plus 10 to the power 10. Neglect. You can keep increasing the temperature. It's only going to change 10 to the power 10 to say 10 to the power 12, 13. Still much smaller. So in this range, when my temperature is not very, very high or very, very low, which is typically the case for the devices, in industry when they make ICs, so typical range is minus 40 degrees Celsius to 125 degrees Celsius. That's the range they usually care about for most of the applications. So in that range, it's going to be flat. What if now I increase my temperature to very high values? What will happen? You are increasing that 10 to the power 10 to 10 to the power 12, 14, 16. At one point, so many electron hole pairs you will generate at high temperatures that now it kind of becomes comparable to the electrons coming from the dopant. So this is where you start to see this knee, and then you keep increasing it. What will happen? The electron hole pairs generated from the thermal energy, they will start to dominate. Correct? And when they start to dominate, what will happen? What will happen to the Fermi level? It's as if you have converted your semiconductor to an intrinsic semiconductor, because that's exactly what happens in an intrinsic semiconductor. Your thermally generated electrons and holes, they matter the most. I mean, there's no dopant, right? So when thermally generated electrons and holes are going to overcome the electron density, say, coming from the dopants, so then Fermi level will also be roughly in the middle. So it becomes intrinsic. It behaves like an intrinsic semiconductor, roughly. Okay? So that's why you have an intrinsic here. Although all of this you can prove mathematically. I'm just giving you some intuitive idea, right? So go through this reading assignment, check the mathematical equations, you can prove all of this through the equations. And then when you have this, when your temperature is very low, again, unless you go to say less than say 50 Kelvin, 60 Kelvin regime, which is usually called cryogenic regime, you won't see much change in the conductivity or the electron concentration. But as you enter that, then you will start to see that your dopants are not fully ionized now. You keep reducing the temperature, what will happen? You keep reducing the temperature, thermal energy to excite these dopant, the electrons in the dopant levels to the conduction band, that energy will become less and less. Correct? Typically, how much energy do you require? 50 millielectron volt, at least that much is required, right? If your energy, thermal energy, say less than that, because how do you determine the thermal energy? Basically, kT, correct? kT is the thermal energy. So if kT value, if I keep reducing the T, the kT becomes smaller and smaller. And for say less than 50 Kelvin, so kT becomes smaller than 50 millielectron volt. I mean, you can check the number, exact number, but I'm just trying to give you some example. Okay, so then your dopants will not fully ionize. You keep lowering the temperature, they will less and less ionize. What will that do? The electron concentration in the conduction band, it will start to reduce, because your dopants are not being able to ionize now. This is called freeze out effect. It's as if you have frozen these dopants, okay, by lowering the temperature. So go through this and let's now move to the next topic. So we have talked about the carrier densities in equilibrium. Essentially, we haven't applied any electric field. So if I do apply an electric field, what would happen? Electron and holes are mobile, right? They can move. We know that. They are not under the influence of the constituent atoms now. So if I apply the electric field, they will move. They will move, so then they will provide what? A current. Some of that we have already seen, but we saw a very ideal picture. In the EK diagram, when I was talking about it, I did talk about it, right? How the electron wave packet moves. So we'll continue from there, but this time we'll get a more realistic picture, right? With what actually happens in a semiconductor.